Hi guys, in this video we're going to cover a derivation for source-free RC and source-free RL circuits. Then we're going to look at the unit for time constant, y equals to seconds. So that's going to be what we're covering in the first video. As we go on, we'll get into solving problems on source-free RL and RC, then derive, step response, solve problems until we get to RLC and move on with the course. Alright, so let's move on. The source-free RC circuits. Source-free source-free RC circuits, R and C. R stands for resistor. I believe you should know what that is. It's look like this in a circuit. So it's simply an element in a circuit. It's a passive element and it impedes charge. It reduces the flow of charge. So the idea is that once you have a resistor in a circuit, once you have more resistors in the circuit, you're going to have less current. So that's the idea. Resistors reduce charge. They impede charge. They work against the flow of charges in the circuits. So you can see they slow electrons down, sort of. That can be a good way to look at it. In a way, C is capacitors. And these are storage elements. Okay, resistors do not store energy of any kind. They don't store energy. They're just currents. They impede currents at all. There's no energy storage in any form. But capacitors, their job is to store up energy. You could say, let's say this is a capacitor in the circuits. It stores up energy. Let's say positive charge powers up here, negative charge powers up here. This is while it's being charged, while the capacitor is being charged up. So as current flows, you get more build up, until it reaches its maximum capacitance voltage, right? V max. So once the current is flowing through it stops, once the current stops, then your capacitor becomes a source. It can now release the voltage it's been storing since through the circuit and back up around until it dies again and the cycle can continue. So resistors don't store charge, denoted by R unit ohms. Capacitors are passive elements. They build up voltage and discharge once current is no longer passing through. Okay. So to derive RC circuits, we'll you start with something like Okay. Okay, and this is our ground, our reference node. I'm going to have a node here. I'm going to have IC flowing this way and IR flowing this way. Okay, remember this is our resistor. This is our capacitor. IC flows this way, IR flows this way. So why is this node here? The idea with source-free RC circuits is that source-free is the response of a circuit by the sudden disconnection of a voltage source or a power source. Alright. I think I misspelled connection. Did I? So what happens is that, let's say you have a source here. Let's say we have a source here. 5 volts. The 5 volt source here at the beginning. Alright, so the purpose of this source at t less than 0 is to charge up our capacitor. Charge it up until it gets to its maximum voltage. So once you remove that source at this node, you're going to have, what's going to happen is now your source-free response. So how do we know it's source-free? When at t greater than 0, we can look at your circuit and say, oh, this is a capacitor, this is a resistor, these are the only components here. So there is no voltage source. Alright, that's how I notice the source-free circuit I'm dealing with, because there's no voltage source at t greater than 0. So once we remove that source from this node, right? Alright, source removed. Once we remove that source, we're going to have current branching in both directions. IC is going to be the current flowing through the capacitor, and IR is going to be the current flowing through through the resistor. And we can use simple KVL. Kirchhoff's, is it Kirchhoff or Kirchhoff? I think it's Kirchhoff. KCL. Kirchhoff's current law. Alright, since we're dealing with the node. So what does that state? The sum of currents entering a circuit, this is sum entering, is going to be equal to the sum of currents leaving a circuit, leaving a node. I'm making a lot of mistakes. So the sum of currents entering the circuit is going to be the sum of current leaving the node. Oh, pardon me. Okay, so let's say we have something like this. Let's call this 1, 2, 3, 4, 5. This is a very brief KCL refresher. Let's say 1 goes in, 2 goes in, 3 goes out, 4 goes out, 5 goes out. Alright, this is what we call a node. A junction where wires meet. Alright, so what happens? Let's say we want to analyze this with KCL. We're going to look at, alright, which of these currents are entering the node? And we're going to see is, alright, 1 is entering, 5 is entering, and 2 is entering. Which is leaving? Alright, we're going to see that, okay, 3 and 4 are leaving. So if we're going to write a KCL expression for this node, let's call it A. For node A, we're going to say I1 plus I5 plus I2 is equal to I3 plus I4. That's the whole idea when you're dealing with KCL. So the sum of currents entering a node is going to be equal to the sum of current leaving a node. Proof. Alright, so that means for this node, we have IC and IR are both leaving the node. And we don't have, okay, this is going to look like, and we don't have any current entering. So we're going to end up with IC plus IR is equal to 0, which is perfectly fine. Now we're going to make some substitutions. From capacitors, we know that the current flowing through a capacitor is C dVdt. Alright, and from Ohm's law, we call V equals to IR. So if I was to find I is going to be V over R. So that's what we're going to do here. So plus V over R is equal to 0. Okay, cool. An important thing to note here is that C and R, the capacitor and the resistor, are going to have the same voltage across them, V, since they are connected in parallel. They both share this node, and they both share this node. So this is a parallel connection. So C dVdt plus V over R is equal to 0. Let's take this to the other side. C dVdt is going to equal minus V over R. Alright. What do we do from here? We're now trying to get together like terms, because this is a differential equation. A simple one, but it's still a differential equation. So for that to work, for us to solve this, we need to get, this is dV, we need to get dV on the same side as V. So we'll be able to solve it. That's the next step we're going to take. So we'll cross multiply. Alright, let me do this in steps. So C over V dV is going to equal minus 1 over R dt. Alright, I hope you understand what happened. I divided both sides by V. So this V cancels out here, becomes 1 over V here. And I multiply through by dt. So dt cancels here and becomes the numerator here. So to make things clear now, I'm also going to do the same for C. So dividing through by C, I'm going to end up with 1 over V dV is equal to minus 1 over RC dt. Alright, so 1 over V dV is equal to minus 1 over RC dt. Simple equation. We integrate from here to see what's popping. The integral of 1 over, when you do mathematics, calculus, let's say you're trying to integrate 1 over x dx. Alright, what you're going to get is ln x plus c. Okay, let's say you're trying to integrate dx with nothing inside. Then what we're going to end up with is x plus c. Alright, let's just leave that by the side so we'll be sure we don't make mistakes with our mathematics. Pardon me, okay? So let's go. This left hand side is going to equal ln v. And that's going to equal, because this is a constant, minus 1 over RC. These have no terms that relate with t, so we might as well bring it out of the integral. And that's going to give us the same thing we wrote here. So that's minus t over RC plus c. Alright, let me bring that together so we can. We call minus T over RC plus, we need an integration constant. C is going to confuse us because of capacitance, so let's stick with K. Alright, what do we do from here? To isolate V, alright, ln V is the natural log. So ln V is log to the base E of V. So E is Euler's number. Euler's number is a special function in math. I believe it's something like 2.718. Yeah, I just checked it. 2.718. So it's log base E of V. So if we were to isolate V, what we'll do is that we'll raise. Alright, let's actually pick another number. Let's say we're doing log base 3 of K. And let's say this is 27. Alright. If we were to solve for K, what we'll do is that we'll raise both sides. We make both sides exponents of 3. We'll raise 3 to the power of both sides. So 3 to the log 3 of K is going to give us K. And that's going to be called 3 to the 7. 3 to the power 27. We'd have to solve that. I'm curious actually. It's a really big number. But you get the idea, hopefully. So that's how we cancel out. So if we want to isolate V, since we're solving for voltage, the purpose of this is to solve for voltage. We'll make both sides exponents of E. So that's E to the ln V is going to equal V, and that's going to be called E to minus T over RC plus K. We're now going to use another integral rule. Remember, A to the M plus N is A to the M times A to the N. Alright, so that's what we're going to use here. So E to the ln V is going to equal E to minus T over RC. Oh, this is V. I forgot to make that substitution. So this is V. It's equal minus T over RC times E to the K. We can make E to the K another constant on its own. Let's call it A. So A times E to the minus T over RC. Alright, so we're almost through. Alright, so we're almost through. What we have to do now is to isolate A in our equation. We can't leave A there. It doesn't mean anything. So what are we going to do if we're looking for A? Remember, V is a function of time. Okay, V is voltage as a function of time. That's going to equal A E to the minus T over RC. So what we're going to do now is we're going to say, alright, let time equal 0. Alright, let's look at what happens when the time is equal to 0. So what do I mean? At T equals 0, remember, for our capacitor is going to look something like, if we were to plot the voltage across our capacitor, it's going to look something like this. Okay? A decaying exponential over time. So this is the maximum value. Alright, and this is V naught, since this is 0. Okay, this axis is time, this axis is voltage. Alright, so this is V naught. So V naught is the time at T equals 0, and is also the highest value of the capacitor. It's also the highest value of the capacitor. So let's see. So when T equals 0, V of T becomes V naught, and that is equals to A times E to the 0 over RC. Remember, anything raised to power 0 becomes 1. So V naught becomes A. Alright, so we can just throw this back into that equation and we end up with V of T is equal to V naught E to the minus T over RC volts. So that's how we solve for the source-free RC circuits.